Target acquisition consists of a ballistic phase and a corrective phase, but the corrective phase is often particularly problematic for users with motor impairments. Not surprisingly, small targets are especially difficult for users with motor impairments, and many such targets exist in current graphical user interfaces. Our solution is to introduce enhanced area cursors, which are target acquisition techniques that reduce the need for corrective phase pointing, lessen the effects of small target size, and reduce the need for accurate, steady clicking. Many techniques already exist to increase effective target size, thus making small targets easier to acquire. The area cursor, for example, makes it easier to select sparsely laid out targets, but degrades to a point cursor when multiple targets are in close proximity. The bubble cursor offers an improvement over the area cursor since it resizes based on nearby targets. However, it still degrades to a point cursor when targets are adjacent. A third example is sticky icons, where mouse gain drops when the cursor enters a target. There are many variations on this technique, but a common theme is that distractor targets can impede performance and can be hard to avoid for people with motor impairments. Here are our 4 enhanced area cursor techniques, which we will briefly demonstrate. All of our enhanced area cursors include an activation step. With the click and cross cursor, the cursor is activated by a single click. All targets under the cursor animate out to the periphery and become enlarged crossing targets. To select one of these targets, the user simply crosses over the associated arc segment and stops the mouse. If they cross over the wrong target, the user can recover and return to the center of the circle without stopping the mouse. If the user accidentally activates the cursor in the wrong location, it can be cancelled with a single click. The cross and cross cursor is similar to the previous click and cross cursor, except for the activation step. Here, no clicking is required at all. The area cursor tracks the mouse pointer, and the user activates the cursor by reversing direction, crossing over the red trigger line, and stopping. The user can again cancel cursor activation by clicking inside the cursor. Accidentally crossing the wrong target can be reversed by quickly returning to the center of the area cursor. Finally, if the user accidentally crosses the red trigger line, they can quickly return inside the area cursor before stopping the mouse, and the activation will not occur. A mouse click activates the Visual-Motor-Magnification cursor, causing the entire area cursor and all the targets underneath it to grow in size. A mouse pointer appears, and the user makes a second click to select a target. Unlike screen magnifiers, which magnify only the visual space, the Visual-Motor-Magnifier allows the user to work within both increased visual and motor space, making it easy to acquire targets for people with poor motor control. If the user accidentally activates the Visual-Motor-Magnification cursor in the wrong location, it can be cancelled by moving the mouse pointer outside the area cursor and clicking. There are also several customization options for this cursor, including using an inset bubble cursor, changing the magnification factor, and dwell selection instead of clicking. The motor magnification cursor uses a mouse click to activate the area cursor, causing the pointer to appear. Here, the mouse gain or speed drops upon activation, and the user selects their intended target with a second click. To cancel an activated area cursor, the user clicks outside of it. The motor magnification cursor has all the same additional features as described for the Visual-Motor-Magnification cursor. We have introduced 4 types of enhanced area cursors based on design goals to reduce fine pointing demands for people with motor impairments. These designs include visual and motor space magnification and extending goal crossing beyond pen-based devices.